Okay, guys. So, welcome back. If you've watched the first video, thank you. It definitely helps. But now we actually want to program. So, how do you program actually with this Pi? What can you program, and how does it actually work? Are the major questions, at least that come to my mind. So, if you've never programmed before, the good news is this is quite easy. We're going to do the blinker tutorial, which is simply turning a light on and off. That's the easiest tutorial. It's what most things start out with. And it's written in Python, which is already installed. Now, if you already know programming, then you may be wondering, well, what can I put on Pi? What can I actually program in? And the answer is that the Raspberry Pi, with the OS that we have installed, which is Raspbian, only comes with Python installed. So if you don't want to download any extras, you just want to use what is already on the Pi, you would be programming in Python. That is what most tutorials are in, since the Raspberry already comes with it. But you're not limited to that, actually. The biggest question for programmers is, well, what can I program in? Am I limited to a language? Is this a chip? Like, how does programming actually work on this thing? And the simplest answer is that you can actually program in a bunch of different languages. You are not limited to just one. Python is what comes with the Pi. It's what I would recommend, unless you already know Python and you want to learn something else. You can, but if you're like me and you're used to programming in Java, C or C# or some other language, but you've never really programmed in Python, and you want to learn a new language, then I definitely recommend just sticking with what's already on here. That is what we will actually be doing. But you do have options. You can actually, if you want to download extras, you can go online with the Raspberry Pi once it's booted up, and you can actually download and install other IDEs. So you can actually program in Python, Java, C#, and other languages. So you are not limited to Python. You can actually use the language you already program in, that you already know. But for those who do not know programming, or those who don't want to do any extras, they just want to boot up into the Pi, then that is Python. And that is what I recommend. That is what the tutorial will be using. But just know that you are not limited to Python. You can use other languages. They just require you to do extra stuff to actually get it installed onto the Pi. So, the last tutorial we went and we installed the OS, got everything set up so that this actually has an OS on it now and can be ran. So in this tutorial, now that we know the basics, we will set it up to actually program the blinker. So there are two things you can do. We will be using the breadboard this time, and you can either set up the breadboard and then turn on the Pi and boot it up, which is the safest thing to do, but I'm not safe. So you can also, as long as you are not running the program, you can hook everything up and then mess with all the circuitry while the Pi is turned on and running, as long as the program is not interacting with the board. And it's perfectly safe, but it's not the safest way to do it. it is the way I'm going to do it. So the first thing you want to do if you're going to follow my way is actually take your Raspberry Pi, which if you're going to write in order of the tutorials is already turned on, but mine is not. If yours is not, you want to hook it up and turn it on, but you want to hook up the breadboard as well, because we will be using it. So I'm going to hook up my Raspberry Pi right now, actually. And the one thing I want to mention while I'm doing this is that you want to hook up the HDMI cable first, or not necessarily first, but before the power is turned on. Because as soon as you connect the power supply, there is no on-off switch, so the Raspberry will boot up. And while it's booting into its Linux mode, it's setting everything up, setting the USB ports up, it's setting the display, everything that's connected. Linux is going through and turning on and configuring. If you decide to plug in the HDMI cable, after it's already booted up, you're going to run into the problem where the screen looks funky. And that's because the resolution will not be set to 1080p or 1080. Because whenever Linux boots up and it doesn't detect that you have the cable connected, it'll default to a lower resolution to, as I guess, a safeguard. I would assume it's a safeguard. Which means your screen will look funky and out of whack. But if you turn it on with the HDMI cable plugged in, it works perfectly because it automatically knows that it can go up to high definition. So make sure you always turn on the Raspberry Pi after this is connected. That way you don't get into funky issues. Now, the Raspberry Pi is actually ready to be turned on. I'm going to go ahead and connect this stuff. So the first thing you want to do is connect the ribbon cable if you have one. If you don't have one, then you want to make sure that you have female ends. So you don't want what I have. You don't want two metal poles sticking out. You want a metal pole sticking out and a hole on the opposite end that a pole can actually go into. If you have the ribbon cable, then you want two of these. So you want two poles. So it all depends on what you actually have. Hopefully you do have the ribbon cable, because it makes life so much easier. The ribbon cable, you just take and you plug one end on just like this onto the Raspberry Pi, right over the holes. Make sure they line up. You don't want to bend any of the things. And then the other end gets plugged right here on the top of this. This is where all the pins come into this board. This one you cannot connect backwards because it has a hole. And if you look on this, it has a bump. So the bump has to align with the hole. So don't worry about getting this one backwards. It goes like this. Just push down and make sure that you're not bending anything, because bending is very bad. Then once you have this lovely dovely labeled thing goes directly on here. Now, you don't have to line up the positive with the positive and the negative with the negative. It makes it a whole lot easier, but you don't have to. So when I first hooked up my Raspberry Pi, I actually hooked it up this way, which if you look, actually makes it so that my positive and negatives are switched. Now, that doesn't do anything. That makes no difference whatsoever. It just makes it more confusing because when you go to read it, it's like, well, is it positive or is it negative? What is it? So you basically choose where you want this to go on here. Now, before you do that, you need to know how the board is laid out. So a breadboard is what this is actually called, even though it has nothing to do with bread. And it's basic electronics. So if you do any type of electronics, before you build circuit boards, which is what that is, you basically experiment and everything else on a breadboard, because you can arrange electronics on this however you want. So it makes it really easy to design stuff. Now, breadboards, the way they work is they have rows that are labeled by numbers, as you can see. This one is 1 to 30. And they go by paths. So, row 1 has every single one of these dots connected to each other. So there are 5. So there are 5 columns. And the way the breadboard is lined up is that the rows are connected to each other. So what that means is you can technically have 5 wires all hooked as if they're connected. So anything that is put inside of this hole, this hole, this hole, this hole, or this hole, so this entire row, is all going to be connected to the same thing, because there's 2 pieces of metal that are inside the breadboard that basically connect every single hole in this row together. They are connected together. So if I basically put a wire in the hole D and the other end in hole A, it's connected to itself. It's basically an entire loop right now, because the breadboard will connect the space that's in between here via BNC. So all you need to know is that each row, so 1, 2, 3, etc., all the way down to 30, is connected the whole way across for each row. The rows, however, are not connected. So if I put something in row 1 and I put it both ends in row 1, it's connected to itself. But if I put one end in row 1 and the other end in row 3, it is no longer connected to itself, because there is nothing connecting on the breadboard side, row 1 to row 3. So just remember that rows are connected to each other. It's basically one straight piece of metal that connects all the holes. But going down, they are not connected. They are connected this way, not this way. But once you get over here, so to the positive and negative, it's actually the opposite. They are not connected via rows. They are connected via columns. So that's what the red and blue lines signify, is that this entire side, this whole thing, is all connected. Every one of these holes on this side is connected to each other. And then every hole on this side is connected to each other as well. But they are not connected across. And it applies to both sides. So this is the same exact thing as this. They are connected down. They are not connected to the side. So if I put something in the first hole here and something in the second hole, they will be connected to each other. Now, there's one last thing about breadboards. We mentioned earlier that the middle is connected by rows. And as you can see, we have columns A, B, C, D, E, and then it continues. It goes F, G, H, I, J. Don't confuse that with it actually being connected, with it actually continuing. It doesn't. That's labeling purposes only. Because this center division right here actually represents where the board is split. So this side is not connected to this side. Even though it tries to trick you and it's like A, B, C, D, E, oh, we're going to continue. The circuits do not continue. So if I connect something on this side and I put the other end on this side, even though these wires are in the same row, they are not connected because nothing is connected once it hits the this little indentation, the division. So you basically have two sides to a breadboard. You have this side, and then you have this side. These two sides are not connected, no matter if you're on the same row or you're on a different row. And the same thing goes for these two outer ones. These two are in no way connected here. They're actually, if you want to bend the breadboard, since it's actually just on a sticky backside, you can actually see that it comes off. It's just something that is slapped beside the breadboard and then labeled. It's not actually connected to the middle part in any way, shape, or form. Now, I know there's some of you, the ones who have never done electronics before. I have actually taken electronics, so this is easy for me to understand, but it may not be easy for you to understand. You may be still going, what the heck? What's connected? What's not connected? What do you mean connected? What happens if it's connected? But the easiest thing to explain all that in a clear way is to actually show you with an example. So we're going to continue. We are going to connect this board to the breadboard. Now, the only way you can validly connect this is if you make it so that this division is in between the pins right here. Because these two ends here are the positive and negatives for 3 volts and 5 volts. So, if you have a kit, they design the board to be just the right size to where this fits perfectly. So you line the 2 prongs either on a 3 volt or the 5 volt. Look at those. Line them up to the second holes. And that's because the first pins of the middle actually go into the first ones. So you place them lightly, then you push down, and you want to make sure that it's even. You don't want to bend any of the pins, because bending the pins is just gonna make things really bad. You do have to push kind of hard. It's not gonna go in simple because you're pushing 44 pins in at once. But you do want to push them down. And you can do this with the Raspberry Pi turned on or off. It does not matter if you continued the tutorial and are just pushing this in with the Pi on. Even though mine's not on, you can do it with it on. So now, you basically, by doing that, have the things connected. So you have the breadboard connected to the Raspberry Pi, which means you can actually program now and interact with the breadboard and anything you connect to it. And as you can see, the only thing that's usable by something other than the pins, so something like buttons, LEDs, lights, sensors, anything, basically has to go in this little tiny space that's below the board that you just connected. So there's not much space, especially since the rows are connected to each other. So you have about 8 rows to actually do stuff with. But now that we have this connected, we are going to actually turn on the Raspberry Pi. And while this boots up, I can get my mouse and stuff ready. And now as you can see, when you turn on the Pi, it comes up, it says it's little Linux stuff, and then it turns around and runs the GUI, the graphical user interface, which basically just means instead of typing commands into a black screen, you actually get to interact with it. So this is the Raspberry Pi when you boot it up by default. Now it's basically acting like a computer, which means you have programs and everything else. It's not just a chip. So if you got a Raspberry Pi thinking, oh, you're programming it on a laptop or something, send the program to the chip and plug it in, have it run, that's actually not what the Raspberry Pi is. The Raspberry Pi is actually a mini computer. So you actually use it just like you would any other computer. So if we open up the menu, default, if you can see this, we have these programs for programming. Scratch is what you will see almost every tutorial on the Raspberry Pi site using, and it's a drag and drop from what I read, which I do not recommend because you're not actually writing your own code. You're letting the program write the code for you, and as a programmer, that's not ideal. So I do not recommend using Scratch, but you can find things that tell you what to do if you use Scratch. We are actually going to use Python 2, which is what we will be programming in Python. This is the program you use in order to program with Python. I don't know why they call the Python IDE actual Python, because an IDE is separate from the language, but we will be using this. There's also, of course, BlueJ and Greenfoot, which you can sit there and use to actually build Java if you want. I do not recommend either one. I have used both, but I did not like them very much, so I would not recommend them. You can open them, of course, and mess around and see all the fun stuff you can do. And if you're interested, side note, it does come with Minecraft, which is quite interesting. But what we're going to do is use Python 2. You don't want to use Python 3. You can if you want to feel adventurous. But they actually vary very big. So they greatly differ, even though they're both Python. And they're just different versions of Python, which is usually a good thing. But Python 3 is actually way different from Python 2. So we will actually be using Python 2. So you basically open it up. And when you open, it looks like a notepad. And it's actually a command line interface. But we don't need this. We need to create a new file. So we are going to click File, New File. And what that does is opens up this untitled notepad thingy. This is where Python is actually written. This is where you actually do the programming. It looks just like you're typing a notepad document, but you're actually writing the program. If you're used to programming and you're used to C#, Java, where you have fancy IDEs, Eclipse, Visual Studio, and all that stuff, this is not actually like that. It's just a notepad. This is the actual IDE that comes with Raspberry Pi. and you basically type out the program and then run it. So what we're going to do right now is actually type out the program and then explain what each thing does, so you're not just executing something you have no idea about. So I'm going to write it and then be right back. Okay, so I'm back, and we've written the program. This is exactly what you will need to write. But I want to explain what it's actually doing first. So go ahead and pause the video and type this up if you want. Or you can type and listen, or however you feel like doing it. But basically, this is Python. So there are a few rules to Python that you need to know before you can even understand what this is doing. If you want something outside of Python, so something extra, you need to import it into your program, because Python will only use what it knows by default and what you tell it about, which is what import is doing. So for this, we're simply making something blank using the pins. So we only need two things. We need Python to know about time, which is what's going to keep track of how many seconds there are, and we need it to know about the pins. Those are GPIO, and that stands for General Purpose Input Output. It basically is just what allows Python to interact and know about the pins. Python is a language that, if you've already programmed and you're familiar with Java or C#, you're used to curly braces, and you're used to semicolons, and basically endings. Whereas Python doesn't have that, and you need to be aware of it. Python is a language that, if you've never worked with it, is actually tab and space sensitive. For example, the while. In C# and Java and some other languages, where it says while true, you would have to put the curly braces or brackets, whatever you want to call them, to begin and end the loop. But in Python, you do not. You actually need only tabs or 4 spaces. So Python is a space-sensitive language, and it uses the colons to basically tell it where something needs to happen. So, for example, the true. Anything after the colon, as long as it's indented, is part of that true. Once you stop indenting, then the file, then that section is done. Once the file reaches the end, the program is done. If you haven't programmed before, then all you need to know is that you need to import things. As long as you're interacting with pins, you always will need to import GPIO. And it is space sensitive, but discard everything I said about curly braces and brackets, because you won't know anything about those and it'll just confuse you. But if you do know about those because you have programmed before, Python does not use them. Now, as far as the program is concerned, it basically turns on and off a light and sets it up. That's all it's doing. So we're going to go line by line and tell you what it's doing. And hopefully you can learn some programming if you don't already know programming, and some Python if you don't know Python. If you know both, well, then you might want to skip this part. So the first two lines are imports, and that basically tells Python that you need to bring something extra into your program that Python needs to know about. So the first one is import rpy.gpio as GPIO, lowercase. And what that does is tells Python to grab the rpy GPO, and we don't want to, every time we want to reference it, we have to type that. We have to either type its name, or we have the option of renaming it. So we renamed it to lowercase GPIO, so that every time we want to reference that, we can just type GPIO, lowercase. And then right below that, we have import time. Time is how Python can do things such as keep track of seconds, minutes, milliseconds, whatever we need it to keep track of time-wise. When we import time, Python automatically gains the ability to know about time, which we need for our program. So all we do is tell Python to import the time so it knows about it. Underneath that, before you can actually use the pins on the Pi, you need to actually set them up. It sounds weird if you've never dealt with programming or anything, especially with pins. You would think that they're already set up and ready to go, but they are actually not. You have to set them up in your program. So every time you want to interact, you have to do this. So we're telling the GPIO to set the mode in the next line to BCM. And now there are two modes that we can set it to. We can set it to BCM, and we can set it to board. So you can say GPIO dot BCM, and it has to be capitalized. Or you can say dot board, which is also all capitals. And the difference between the two is when you look on the board. So, if we're looking at this board, BCM essentially tells your program that whenever you use the pin numbers, you are going by the printed number. So, pin 4, for example, if you want to use this pin, your BCM says use this pin as number 4, because that is the number that is printed on the board. So whatever number is printed on this board is what your program will actually use, regardless of what pin it actually is. Now, board, which is the other option you can use, is the exact opposite. Instead of using the numbers that are printed on the board, it uses the true pin value. What that means is, this is pin number 1. If the board was blank, if it had no writing on it, this would be pin number 1, and it goes left to right down. So it'd be pin 1, pin 2, pin 3, pin 4, all the way down. And that is what the number system board uses. Board does not use what is written on the board. It uses the true pin numbers. So for pin 4 down here, in BCM, this pin is number 4. But in board, this same pin is number 7. So you get to choose how you want the program to actually identify each pin. You can either have it identified by what's written on your board as the pin numbers, or you can identify it by the true pin number. It's totally up to you. And we are using BCM. So that essentially means we are using the numbers that are written on the board. The next thing you need to do is you need to set up each pin that you are going to hook something up to. For this program, we are starting out with a simple blinking light. The light is one pin. So all we have to do is set up one pin. So GPIO.setup tells the program what you're going to use each pin as. So we have pin 14. And now that's going by what's labeled on the board. And if you aren't sure what pin something is, there are charts online that you can pull up of what the pin numbers are, and easily get the correct pin number. Or you can switch to board mode and go by the true pin number. But setup essentially says either in or out. We are using output because we are sending signals from our program to the light. The light is not sending signals or any type of input back to the Raspberry. The Raspberry is sending signals out. So that's how you can think of in and out. If you are sending a signal from the Pi to something, that is an out. If you are sending a signal from something to the Raspberry Pi, then it's in. So that line essentially says pin 14 is going to be an out. We are going to send signals out from that, and we are not going to accept any in. The next line is the main heart of the program. So once we have everything set up, the pins are set up, we've imported what we need, we are doing the actual program. So while true is an indefinite loop, meaning it will continue to run until you force it to stop, until you exit your program. It's an indefinite loop that does whatever is indented that's below it. Once the indentation stops, the while loop is done, and anything below that is executed after the while loop, which in our program is nothing, because an indefinite loop wouldn't have anything below it. But we are basically forever turning on a light, sleeping, turning off the light, sleeping. And it just keeps doing that cycle indefinitely. Now, there are two things that we are doing inside that loop. We are controlling the light, we are sleeping the program. Now, GPIO.output is how you control something that is on a pin. You can either say high or low in order to turn something off and on. If you know programming, you can think of that as 0 or 1, true or false. It is either on or off. So the second you say dot output, it takes the pin number, and then it takes what you want to do with it. Do you want to turn it off, which is high, or do you want to turn it, do you want to turn it on, which is high, or do you want to turn it off, which is low? And then time.sleep, if you don't know programming, is Python's way of halting your program. Whenever you sleep, you're literally telling your program to stop executing, stop working for however many seconds you put inside the parentheses. So, if you already know programming, you would be wondering, well, what goes inside that sleep? Well, what goes inside the sleep can actually be an int, so it can be 1, 2, 3, 4, 5, or it can be a float, which means it is not specific. You can say 1, 2, you can say 0.1, 0.2, 1.5, however many, whatever you want to put in there. And it represents the number of seconds that your program will halt. So, in English, we are saying turn on turn on pin 14. Then once you do that, halt the program for 1 second. Then we turn off pin 14 and immediately halt the program for 1 more second. And then we do that indefinitely until the program is done. So that's everything that program is doing. It's simply importing, setting up the pins, and then creating a loop. While true is simply an indefinite loop that turns on the light, sleeps, turns it off, and sleeps again. So now that we have the program written, we need to actually set up the board. So this is where I mentioned earlier, where you can either unplug this cable so that you're not messing with the electronics with the Pi on, or you can just sit here and do it anyways, as long as you're not running your program, which I have not told you how to do, so we are not doing that. So it's safe to mess with this. Okay. So, what you need now is one light, whatever color you want. If you have a kit, then the light already came with it. And then you need a resistor. Resistor is the little tiny things, and if you don't know electronics, I'll give you a quick rundown right now of what each one is. So here's my kit, and it comes with a whole bunch of wires and stuff, a resistor color code. This, if you don't have it, this is what I was talking about earlier, where it says what each pin is, and then what they represent. So, for example, pin 14, GPIO 14. This is what pin we're going to use, because we're using what's labeled on the board and not what the true pin value is. Otherwise, it would be 8. So, but if you look at your board, if you have one, it will say TXD. It will not say 14, but it's still pin 14. It's just the board actually says TXD. So keep that in mind. But we have wires, and then we have some lights, some LEDs, and then we have resistors. These are resistors, and they actually do what their name kind of implies. They resist electricity from flowing. So essentially what that means is if you have 3 volts, like we have 3 volts, and we put a resistor on it and connect it to the light, the electricity that flows to the light, as long as this is connected, will not be 3 volts, because this lowers the electricity that is flowing. So instead of 3 volts, depending on what resistor you actually use, you get 2 volts, you get 1 volt, 0.5 volts, But the point is, a resistor lowers the amount of electricity that flows by creating resistance, which is why it's called resistors. So you need a resistor, and you need a light. Now, I have multiple lights. You can use any light you want. And you can use any resistor values you want. But you want to use around 100 ohm resistor. Now, if you have no idea what I just said, and I'm speaking gibberish, what that means is each resistor has its own value. So it has a measure of resistance, as you will. Resistors are measured in ohms, and the higher the number, of course, the more resistance there is. So, the higher the number, the less electricity is allowed to go through. There are colors. If you look at a resistor, there are 4 stripes, or 5 stripes, and they basically tell you exactly how to read the resistor and come up with its value. It's quite simple. You take the first stripe, find its color number, the second stripe, find its number, and then that's the value. So if it had 2 yellows, it'd be 44. And then the third stripe, you find its its value, and that's the multiplier. You take the number that you got from the first 2 stripes and multiply it by whatever value that color represents. So if you had 2 yellows and a third yellow, you would turn around and it'd be 44 times 10. So it'd be 440 kilo ohms. Since there's a K there, it's 10K times the number that the first 2 create. So it'd be 440 kilo ohms, because 10 times 44 is 440. The last one, you don't really have to pay attention to. It's just the tolerance. It's just the percentage that this number is allowed to be off by and still be a good resistor. It's not something you really have to pay attention to, but that's a quick rundown of a resistor. That's what the stripes mean. It's simply the value. And we need something that can resist the flow of electricity, but not by a whole bunch. So you need around 100 ohm to 200 ohm resistor is the ideal. Of course, the higher the number is safe to use, it just lowers the amount of electricity, so how bright the light will be. The lower the value, though, you start getting into danger zone. Or you could try without a resistor, not recommended. So that's for a resistor. The light, really quickly, is an LED, light emitting diode. And it's simply the little tiny lights that are becoming quite popular, and last really long and are really small. And in order for them to work, you have to know which side is negative and which side is positive, because the electricity in a diode can only flow in one direction. If you reverse if you put it in backwards and you reverse the positive and negative, you'll actually blow this. The second it goes to turn on, it'll pop and possibly smoke, and you will have a broken light. Now, to make it easy for people to tell which side is positive and negative, an LED on its 2 feet has a shorter end. So if you look, one end is shorter than the other. That's how you tell what's positive and what's negative. The negative is always the short leg. The long leg is always the positive. So that means that for this light, that the left side, this side, is positive right now, and the right side, this side, is negative. So you can always look at the feet to tell you exactly how it's supposed to be connected. Now, as for the circuit, we are going to make a very simple one. All we have to do is literally hook up the LED to two different rows. It doesn't matter which rows as long as they are not being occupied. So we are just going to, for simplicity, put it right here. All you have to do is put it in and push down a little bit, and that's it. Don't push too far, you'll go straight through the bottom, because the legs are kind of sharp and it will puncture the bottom of this, because the holes in the board go straight through. So don't push too hard. It just has to be able to sit in there. Make sure you know which side is negative and which is positive. This, for mine, shows that row 23 is the negative, row 22 is the positive, so negative, positive. Now, you have to actually connect the light to the pins. So we chose pin 14, which, if we look at the board, is the TXD. Remember earlier I said some pins are not numbered, but they actually say something else. Pin 14 is an example. The board says TXD, it doesn't say 14. So we can choose any pin on that row for row 14, because remember earlier I explained that they are all connected. The holes in each row are connected, so it doesn't matter which one of these holes I put it in, as long as it is on row 4, because row 4 is connected to pin 14. And then we want to put it and connect it to the positive end of the LED. The positive end is on row 22, so we can put this other end on any hole that is not taken up on row 22. As for the resistor, I have this kind of resistor. We're just gonna connect it straight to, from the negative side straight over to the negative side of the LED. For me, that's row 23. For you, of course, it would be different unless you mimic exactly what I just did. And you want to take it to the negative. You can either put it on negative 3 volts or negative 5 volts. It doesn't matter which negative side you put it on. And I'll show you right now, just in case you don't believe me. If I put this on the negative 5 volts and then connect it to the negative LED, you can see it lights up the LED just fine. So it doesn't really matter which one you do. And the light coming on is normal because since we chose pin 14, it's a pin that's normally already in use for TXD. So your light can come on or it can stay off. Every time I've done it, the lights come on, so if your light comes on, it's perfectly normal. Do not fret. But as far as the circuit goes, that's all it takes. And in case you're wondering, well, why isn't it blinking? Well, that's because we haven't actually run the program. So right now, electricity is flowing to the light bulb, but there's nothing telling it to turn off. Which is where the program comes in handy. So, how do we run this program now that we have this circuit actually set up? Well, first, we have to save this file. So I've already saved it as blink.py, as you can see. But you would come up here, do a save as, make sure you remember this location. So /home/pi is where I'm saving it to. You can call it whatever you want. I called it blink since that's what it's doing, but you have to make sure that the file name ends in .py. It has to end in py, because that's the Python file extension, and that's what Python is going to be expecting whenever you tell it to run. So click save. Now, of course, I already have it, so we're just going to say no. And then once you have this saved, that's all you need to do with the file. You can leave this open so you can quickly edit it and change the program to whatever you want. You don't need to close it. I'm going to minimize it because we don't need it. The next thing you need to do is open up a terminal. A terminal is the command line that is going to allow you to actually execute your program. So if you click that, it'll open this. Now, a terminal works by having a user, which the Raspberry Pi automatically defaults to being called a Raspberry Pi, and the user is Pi. So you are Pi at the Raspberry Pi. And then after a $sign is where you type your commands. So we're going to type sudo, which means to run a program or open something, essentially, in an elevated user environment, which means open or do something as the administrator or someone with the highest privilege level. Then we're gonna tell it to run Python, because we're running a Python program. And then you can either type the full path to your program, to the file, or if you don't want to have to type all of that, if we come back here and before doing this, do a change directory. That means change the folder to the folder that you know the file is located in. Then instead of having to type that whole path more than once, like every time you want to run it, we can come in here and simply tell it to run the file. So in my case, it's blink. So blink.py. Now, you'll get a message almost every time, And it will tell you that the channel is already in use, but it's continuing anyway. That's because we're using pin 14 and it thinks that it's technically already in use, but we don't care. We're overriding that. And as long as you don't see any errors, you are running your program. You can tell the program is running because the block symbol is there and it's not doing anything. That essentially means our program is running. And if we look, it's actually blinking. And that's it. You now have a light that is blinking. It will continue to blink forever at 1 second intervals until you end the program. And that's it. And if you're wondering, well, what's actually going on, what's going on is that the pin, in this case, since it's an out, is positive. And it's sending signal or electricity. It's sending electricity down to the light, which is coming across here, going to the resistor and exiting. And that's how the entire thing is working. It's simply sending electricity from this pin to the light bulb and then back. And it'll keep blinking and doing that. And voila! Just like that, you have written your very first program. If yours does not work, the most common culprit is actually the I in the import in the first line, where it says import rpi.gpio as GPIO. Everything is capitalized except for the I in that line. It's capital R, capital P, lowercase I, and then the rest of the GPIO is capitalized. So if you're getting a thing that says error, this import is invalid, it's because most likely you have capitalization issues with the I. But other than that, that's it. So now you have one light blinking, and you know the basics, so you can either mess around and make it blink faster, make it blink slower, turn it into a game, or you can continue on to the next tutorial where we will expand upon this whole blinking thing and make it even better than it already is. But for right now, if you go into back here on the Raspberry, hitting Control-C will cause your program to end, and you'll be brought back to this. It'll tell you that you canceled it with the keyboard, and you can come into your file, which is why it's a good thing to actually leave it open. And where it says time.sleep, try changing that to values. See how fast or slow you can get. Don't just use 1 second. Turn it into 0.5 seconds, 0.05 seconds. That's quite fun. 1 second, 2 seconds. Mess around with the values and actually see what you can get. For example, we're turning it into 0.05 right now. Because whatever you put here is how fast it's going to blink. So you can also try changing the port numbers. Change it to a different port on the board and then update the port numbers here. There's a couple of things you can do with just this one blinking light. The funnest, of course, is to make it go faster. So all you have to do is save the file, just hit Control-S, and then the good thing is, all you have to do is hit up. Just click on the terminal, hit up, and it'll automatically give you your previous command, hit enter, and then you can look at the light bulb. And that is what 0.05 will give you. You get a nice quick flasher. So mess around with that. Make the see how fast you can get it to go. At one point, it actually stays on. While it looks like it's just staying on, even though it's blinking. Find out what value that is. And then when you're ready, continue to the next tutorial, and we'll make this even better.